equations of lines and planes in the two-dimensional case. So on the OXY plane, we can write the equations of a line if we are given the coordinate of a point that is on the line, and if we know the information of the direction of the line. For example, if we know that the point P is on the line and the line is parallel to V, to a vector V, so we know that the line has to be this one. So we know that the line is parallel to V and passing through P. So say this line is L, and we can find the equation of L. So the first type of equation for L is called the vector equation. That is, we use a single vector equation. So an equation that involves vectors to describe this line. So to describe the line L, we describe the coordinate of any point Q living on L. So say Q, pick an arbitrary element Q, here, there, and so on. Say Q is here. We can compute the coordinates of Q, or in other words, we can compute the component of vector OQ. So if we know vector OQ, we know the coordinates of Q. Vector OQ can be computed via OP plus PQ. OP plus PQ. OP and PQ. So the vector equation of the line L, vector OQ equal to vector OP plus vector PQ. Vector OP is known if we are given the coordinates of the point P, and PQ is parallel to vector V, since PQ is parallel to V. This means there must be a scalar. So there is a scalar say T, say a number, a real number in T, such that PQ equal to T times V, right? So that is PQ is parallel to V. So there exists a T such that PQ equal to T times V. And this gives us OQ equal to vector OP plus T times V. And this is the single equation that describes the line L, and we call it the vector equation of L. There is another type of equation that describes the line L. We call it the parametric equation. So that is the equation where we break down the vector equation into its component parts. So instead of having vectors, we will describe the component of the vector. So let's say P has a coordinate x0, y0. P is a vector AB. Then the parametric equation can be written as follows. OQ, say Q has a coordinate x, y, and we want to describe x, y in terms of x0, y0, and AB, and the parameter T. Okay, so T in this case is the parameter. So vector OQ is x, y, right? O is your origin. OP is x0, y0, and t times v is ta, tb. So the vector equation now can be written as, say, star now becomes x, y equal to x0, y0 plus t, a, b. And this is equivalent to x equal to x0 plus ta, y equal to y0 plus tb. And here t we call the parameter. Say t is a parameter. T belongs to the real number set. So this system of equation we call it the parametric equation. Of the light L. And we can do the same for the three-dimensional case. For three-dimensional case, say if we do the same thing, if we have a point P and a vector V, so a light L passed through P and L's parallel to V. Say for example, our vector V is here. Then the light L's pass through P parallel to V is this arbitrary point on L. So Q is an arbitrary point on L. Then we can compute vector OQ by OP plus PQ, and we do the same thing as we did in the two-dimensional case. So PQ is parallel to V. Vector PQ is this vector. It is parallel to vector V. So we know that PQ equal to T times V. So where T is a scalar or a real number in this case. So this gives us OQ equal to OP plus T times V. And this is the vector equation of L. Now we will find the parametric equation for L. X0, Y0, Z0. Then the vector equation becomes OQ. Then the vector equation becomes X, Y, Z equal to X0, Y0, Z0 plus T times V, where V, say, is a vectors A, B, C. A, B, C. So here's T is a parameter. This is a real number. So So here t is a parameter. So this gives us x equal to x0 ta y0 tb and z0 tc. So each value of the parameter t gives a point in each value of the parameter. Gives a point. X, Y, Z on L.